In the last lecture, I quickly took you through a toy example in which we implemented ordinary least squares regression using Pytorch. And now we are going to implement ordinary least square regressions with real data. And by real data, I mean the kind of data you have in CSV files, because the chances are if you work with a regression problem, your data are more likely to be presented to you as a CSV rather than a NumPy array. And obviously, in the last lecture, I just quickly took you through the different steps, but now I'm going to unpack the steps a little bit more. So you can import pandas as PD, NumPy as NP. From Torch AutoGrad, import variable. Now this is something you're going to, this particular package is something you'll encounter a fair bit now and then. So basically, the AutoGrad package provides automatic differentiation for all operations on tensors. And remember, if you remember the theory of ordinary least squares regression, then carrying out ordinary least squares regression and computing things like gradient descent, etc., that does need differentiation, or rather partial differentiations. That's taken care of by this particular package. And variable with a capital V provides a wrapper for the tensor. So I've read in this particular data set, actually let me just read these in. I've read in this particular data set cats m.csv, and this one, it has data, and I've stored the variable, stored these data in the variable called cat.head, and this is an ordinary pandas data frame, and it has data pertaining to the sex of the cat, the body weight, and the height of the cat, and by that I assume its length. And obviously we can use ordinary least squares regression to derive a relationship between them. So right now I'm just going to isolate the numerical variables in the variable called cat2, and essentially this is how you select specific columns. So I'm interested in deriving a relationship between BW2T and HWT, and I want to, and in order to do so, I specify the variable cat, 2 square brackets, BWT and HWT, and these will be stored in the variable cat2. And I'm going to isolate the first column like so. So I use the function .iloc, which can be again implemented on a pandas data frame, and this is going to isolate the first column for me, and you'll see why I've done that. So this is the column BWT of cat2, because in cat2, if I just show you what it is, the first column is BWT and the second one is HWT. And since in Python the indexing starts from 0 and 1, so this is 0 and this is 1. And the data type is float64. So now if we want to implement linear regression on these kind of data, the first thing we have to do is to convert pandas columns to NumPy arrays. So this is my variable x cat to iloc, and that isolated this particular entity column BWT for me. So when I say dot values, and I'm going to run that right now, and I print it, this has been converted to a NumPy ND array. And similarly, I want HWT to be my y variable, so I create a variable y, cat2.iloc, I specify 1, which will essentially isolate the second column because of the scheme that we follow, 0 and 1 values, and it will convert the values of the second pandas column to NumPy. So, and NumPy ND array. So when I convert my X and Y to NumPy ND array, I can convert NumPy to tensor, and by that I mean the Pytorch tensor. So X underscore NP dot array, I'm going to convert it to data type float 32, carry out reshaping like so, and then X underscore tensor. So I call the function variable because this is going to act as a wrapper, torch from NumPy. So basically from NumPy, I'm going to convert it to a torch kind of a tensor and put in this NumPy x underscore np, and I'm going to do the same with the y. So I get two variables, x underscore tensor and y underscore tensor. And then I can import torch nn dot as NN, and NN stands for neural networks, and it may sound strange to you, why am I talking about neural networks here? And we are going to work a lot with this package later on, but yes, we can call NN and use that to implement linear regression as well. So I define a class linear regression NN.module. This is a super function because it's def underscore init, self input size output size, super linear regression, which I call from nn.module self init initialize, self.linear nn linear input dimension output dimension. And that's what we are going to return. Now we can define the model. My input dimension is 1 because I just have one response variable, and the output dimension is also 1 because I just have one predictor. Model, linear regression, input, output dimension. Now we are going to calculate the mean square error, which is our loss function, MSC. I'm going to store the results in the variable MSC, nn.msc loss. So from nn, I'm going to call MSC loss. Now we are going to do optimization. So this is the learning rate, which I spoke about before, or alpha, and I've just set it at 0.02. And for optimizer, we use the gradient descent function, or in this case, the most common one is the stochastic gradient descent. So torch optim SGD, model.parameters, because it's the model parameters that we have to optimize, and with this learning rate so that we can identify the local minimum. So again, what I covered in theory, those are things that you don't have to implement from first principles, and you can see all of this has been in a way implemented for you. Train model, loss list, we are going to go through 1000 iterations, and indeed you can have as many iterations as you want till you get the desired accuracy. For IT in range iteration, so we are going to run the following code, this entire code, 1000 times. So that's what the for loop does. So for this 1000 optimizer, this is the 0 grad because every time we'll just set it back to 0. Forward passed result model X tensor. So we are going to implement the linear regression YMX plus C, and this is the linear regression model, and to that we feed the predictor variable. We are going to calculate the loss by comparing the result, this particular result, which is going to give us the predicted y. So we'll obtain the predicted y with the actual response variable, and that will give us the loss. And this is a backward propagation algorithm, loss.backward. Here we are going to update the parameters, optimizer step, append the loss in a list. So this loss underscore list, square brackets, basically this creates a vector with an empty list, and we are going to add our results here. And then we are going to print the loss for every 50th iteration. Let's make it 50. Okay, I need to run some of these code chunks again. So 0, 50, and this is the loss we get at 0, and we have to minimize the loss, and we can see that we are not getting a lot of minimization of our loss, and that's pretty constant. So now we can just plot our data, and we can see after the 0th iteration, the ability to reduce the loss is not particularly great. So maybe we don't need so many iterations. I create a variable predicted, and I'm going to feed xtensor to it, and now we can actually compare the predicted response variable with the actual response variable. So this is the original y and this is the predicted y, and they're frankly quite far off, and ordinary least squares regression is not the best machine learning algorithm ever, and the purpose of this lecture is actually to introduce you to some of the most common concepts like loss functions and gradient descent, because these are things that we are going to encounter, and some of the packages that we saw here, especially the NN package, are things that we are going to encounter further on in this course.